In the supreme name of Almighty Allah. Thank you, Mike, and joining the third lecture. At glance, if we see, this is the last lecture of the remote sensing principles. Okay, so we covered so far the electromagnetic radiation. We covered the Earth observation platforms, and now we are discussing the Earth observation instruments, which is one of the core part of the platforms. So the next lecture will be in glance totally changed. That will be the remote sensing products. So starting lecture will be the remote sense, remote sense data or remotely sensed data. You can say them or remotely sensed. Okay, so we are starting with the sensor. The last lecture we discussed about the platforms and instruments. We assume or we consider the sensor as a part of the platforms. At some time, the sensor by itself can be called a platform, including the sensor, but usually we define the sensor as an instrument of the platform. So, sensor is the Earth observation instrument. A sensor records incoming radiant power or radiance and turns electromagnetic information into data. This is the simplistic definition how they are working. So we have multiple types of sensor. Some of them are generating their own uh, pulse, and the normal satellite, they are capturing the radiance and measuring the information from the electromagnetic wave. Okay, so the core meaning is records incoming radiant power or incoming radiance. Okay, if we see the example of the solar power or solar radiance, so the sun is the originating the sunlights. In this, when it's bounce back to the sensor, so they are trying to capture that electromagnetic waves, and then they are deriving the information from that. Can means only the sensing instruments or the whole acquisition system. As I said in the initials, that this sensor can be also called a complete a platform, and also the sensor can be called, I mean, whole can be called a sensor, like it includes also the platform, but usually it's also can be a part of this whole platform. Different sensor collects different physical information from the same target. This is the core idea of the whole lectures. We will be discussing multiple types of sensors, and every sensor has its own physical information, and they are collecting a certain physical information from the target. And the target is very obvious. We mentioned in the previous lecture also the land. So from the land, we are capturing multiple information as required. Platform carries the sensor, the instrument measures the signal. This is the basics. Okay. Okay, the first one is the active and passive sensors. So this is the operation mechanism of the sensor. We are dividing the sensor on a two types. We can call them active and passive sensor. We can divide the sensor based on the domain of the spectral domain. We can call them the visible, infrared, microwave, and many more. And we can divide them based on imaging or non-imaging, radar imaging. And we can also divide based on the information collected, like reflectance, the height, size, and temperature, and many more. But we will be mainly discussing the three main categories based on which we are dividing, and the main category will be active and passive. The main category is active and passive. We are dividing the sensor, but here we are also having two more categories. I mean, like imaging plus non-imaging outputs. So the output is divided, like sensors are categorized on the imaging output and non-imaging output, and passive and active operation mechanism, which we are discussing right now, and based on the domains, as we discussed that. It can be divided or categorized the sensor based on the visible, optical, infrared, or microwaves domains. So there are multiple domains. We are discussing the active and passive sensors. The first major distinction is whether the sensor creates the illumination radiation or not. So for the normal satellites or the classical satellites were capturing the solar radiation, and we have another type of sensor also that they can generate its own illuminations based on what they would like to light the target and capture its information. So that's why it's called active sensors. And the passive sensors are in the case of that they are waiting for the day to have the sun, and the sun is illuminating the objects on the earth or the targets on the earth. And after that, with the originates, and then the bouncing originating radio signals they are capturing, or electromagnetic waves they are capturing. So in the active sensor case, the sensor comes with an electromagnetic emitting devices which illuminates the target. If we see this picture, in this picture, the having its own emitting device, okay, which illuminates the target. The picture visibly clearly shows that they are sending their own emitting signal, and they are bouncing with the target, and they are going back to the sensor. So needs in no external sources can operate from the day and night. And these kind of sensors are really good that they are not dependent, but the higher complexity and higher consumption, this is one of the cons you can consider. So the example of the active sensors are radar, lidar, fluorescence sensors. So these are the examples of the active sensors. In the passive sensors are realized on the external emission of electromagnetic waves. So electromagnetic waves is nothing but the solar radiation. Needs an external emitter, the sun or the target itself. So it's not necessarily the own, okay, like it could be also possible that the target itself can emit their own electromagnetic waves. It depends upon the objective what we are measuring or what we would like to look into. Lower complexity in energy consumption. That is the benefit in comparison to the active sensor, because active sensors is having higher complexity and higher energy consumption. But here in the passive sensors, it is lower complexity and higher consumption, and energy lower consumption. And both of them, the complexity is also lower, and the energy consumption is also lower, and complexity both sides. But they are dependent. It can only work in the day. It is dependent on the target itself, emission or the sun. So the examples are multispectral opticals, hyperspectral opticals, microwave spectrometers, night light sensors. So these are some of the examples of the passive sensors. So this is one of the main categorization. We are categorizing the sensors. Then we can divide by the domains, okay, and we can also divide by the imaging or non-imaging radars. In the fourth one, which is not mentioned here, that is also possible by the information collected by reflectance, by height, by temperature, by moisture. So these are other ways to categorize them. uh, Actives is basically they are emitting and receiving, but in the passive they receive external emission. That is also the smallest difference and differentiating the definition. Active sensors, now we are discussing the first one. Okay, that was the categorization, and here it is now a little bit more detail about each one. Active sensors, they carry an electromagnetic emitter, illuminate the target, and measure the return signal. The when the signal is returning, it's almost the same. But the good point in the active sensor, they have its own emitting electromagnetic emitter, and they are illuminating the target. Even that's why it works at nights also in receiving the return signal. This is the simplistic operations of how these active sensors are working. Generates the radiation used to illuminate the target. So they are generating their own illuminating emitting electromagnetic emittance to illuminate the target. It do not need sunlight or other external sources in this case, as like in the passive sensors can operate during the day and night. We discussed already as higher system complexity and higher consumption. Yeah, the air consumption is very high in terms of energy, and it's also very complex. Examples we have seen like radio detection and ranging, radar, and LiDAR, light detection and ranging, and fluorescence sensors. So the main strength is the controlled illumination in all-day acquisition. That's a really powerful option we are having here in case of passive sensors, which only works in from the day side, so they can work all the day acquisition. Active sensors. The sensor comes with the electromagnetic emittance devices and which illuminates the target. This is an example or the same details again repeating, and needs no external source, can operate in light, in the same things again repeating. This picture represents this topic very well. If we see the radar and the area they have covered, the gray color, that shows that they are emitting the target, and they are trying to illuminate the target with their own electromagnetic emitter. So, and their back signals are bounce back signals are trying to be captured by the satellite again. So from that side, the signal is also coming. From this side, the signal is also going. So one of them is the incoming electromagnetic emitter signals, and the other one is the back bounce. Now let's move discuss the passive sensors. They rely on the radiation already available from the sun or emitted by the target itself. So the passive sensors is working on the mechanism of the solar radiation or the emittance of the target itself. So receive external electromagnetic emissions, and illumination source can be sun or the target's own thermal emission. Thermal emission, basically, we discussed that the target can itself can emit their own radiance. It is basically the thermal emission of the target. And thermal is mean temperature. Load complexity and energy consumption in the active systems. So it's not obvious we can say active sensors are good or passive sensors are good in a clear, crisp cut way. Both of them has its own benefits and pros and cons, and they have their own applications. So a passive sensor is also required, and the active sensor is also required. Examples are multispectral optical sensors, hyperspectral multiple optical sensors, thermal sensors, scanners, sorry, microwaves, microwave radiometers, and night light sensors. So in this case, we are also having the passive sensors, but which can work the night light sensors, but specifically using for the weather operations. We will discuss these some of the examples. Many illuminations are the many passive optical sensors depends on illuminations in clear atmospheres. We already discussed the atmospheric window in the first lecture, which is really important concept for the passive sensors. So the passive sensors are mainly dependent on the illuminations, and the second thing it is the clear atmosphere. So the clear atmosphere is also affecting because if there is a higher absorption and higher scattering, so the signal cannot be or the electromagnetic waves cannot be bounced back to the sensor, and they cannot be captured. So this is one of the limitations you can call them in the passive sensor, and but they have some also benefits. Move on. So here we are gonna see the categorization ways, how this is categorized. So sensors combines the operation mechanism. So the operation mechanism is active and passive operation mechanism. We discussed already in detail. The wavelength, okay, wavelength is another one like visible, optical, infrared, microwave domain. So you can call them wavelength range or the domain range. and type of information collected. Yeah, this is exactly the type of information I was talking about. The type of information we are collecting either is a reflectance, temperature, moisture, height, multiple things we are having. Is information collection, so we are categorizing the sensor. And the another way is imaging in non-imaging output. So these are the two another options based on which we are differentiating the categories of the sensors. The instrument choose determines what the image or measurement can reveal. This is really important information. The instrument choice is really important in the determining how the image or the measurement can be revealed. So all applications are dependent on the instrument we are choosing or requirement we are having. So based on that requirement, we are choosing or selecting the certain instrument to capture certain kind of acquisitions or measures need to be revealed. In the below side, this categories of a sensor has been given in the reflecting how all the combinations of features can be observed combined in perspective of the operation mechanism and the wavelength size in the passive or active. So active sensors are not that much, but we have multiple passive sensors. If we go back and if we see the active sensor examples are the radar, like radio detections and ranging in LiDAR, which is light detection and ranging in fluorescence sensor. But if you see the examples of the passive sensor, they are multiple. Each sensor will be discussed in more details further we are going. We are having the examples of multiple spectral sensors, hyperspectral sensors, microwave radiometers, night light sensors, and the thermal sensor. Thermal sensors are used for detection of the temperature. We have seen what is sensor in some of the categorization. The main categories which we are taking in this course, that is the active and passive sensor strategy, and we are differentiating based on the this thing mainly. We are starting with the photo camera and video cameras. And so it is CCD based charge couple device. And this is working under the 400 nanometer, uh, greater than the alpha, and alpha is less than 900 nanometer. Nanometer. This is the wavelength we are representing. In this application, we can see in our phones. Okay, photogrammetry or mapping. This is the exact idea, the same uh, sensor kind of sensor they are using. And here we have given some of the examples of the such kind of 400 nanometers or the 900 nanometers examples. So this is photo camera charge couple device, and it's working under the 400 till 900 nanometer mapping and photogrammetry. And video camera recorder, we have some satellites, they are also recording the images, videos. So that is, I mean, they are taking a very short clip with the high resolutions. So this is the photo cameras and videos. So cameras collect visuals and near infrared scenes, and with videos, cameras also capture temporal sequences. So one camera is for taking of the visuals is actually near infrared scenes, but the video cameras are capturing the thermal information or the temporal sequences. This is the photo cameras and video cameras. Now, this is the second sensor, which is multispectral sensor. They measure the radiance at a selected wavelength bands rather than the full continuous curve. The idea behind the multiple spectral sensor is they are taking the multiple acquisition of a same area with multiple wavelengths, and that's why they call multispectral sensor, and not with one full continuous curve. It is a point-wise measurement. Point-wise mean like exactly on certain point we are taking the acquisitions with multiple bands. or multiple wavelength, but the wavelength different the wavelength measurement inside the one another, and the height of the wavelength is not that much different. And if you can see, the multispectral means like multispectral bands, multiple spectral bands, and typically bands are 4 to 8, and the bandwidth between the bands are 100 nanometer, which is very less. And in the next one, we will see that is the hyperspectral sensors, which is more even smaller than like 40 to nanometers, and that's really more clear version, and that's why they call them hyperspectral sensor. And this is used mainly for the multispectral sensors or multiple spectral bands for the land cover and vegetation analysis, water, soil mapping, and thematic classifications. Okay, the sensor samples the spectral response at several key position. So the idea is like mm, what we see in the right side in the pictures of the vegetation reflectance. It is exactly they are showing that the acquisition has been taken at several key positions with a multiple wavelength. So this is the idea of the multiple spectral sensors. The multiple spectral sensors uses also in the true color and infrared false colors. So true colors, you can also take this as a comparison of the true color versus the false colors, or we can also call them the false color is not like a fake color. Actually, it is like infrared colors. You can also call them this way. So the color composite translate the spectral bands into the display colors. So this is exactly the translating the spectral bands. The actual acquisition which we are having, they are matrices or the numerical values. Later on, we are converting them into the pictures or putting the colors of RGB, which is visible to human eye, or gray level values. So true color means actually red, green, and blue. In the false color, which is this is visible by human eye, which is starting from 0.4 to 0.75. This is the range of the visible in the visible range of the electromagnetic spectrum. And the false colors are nothing. It's a near infrared displayed as a red colors. If you see in the Sentinel-2 image has been taken of the multispectral pictures, looks like near to some region of Pavia. So this is the true colors in infrared false colors differentiation in terms of the multispectral sensors. And this is an important concept relevant to that. So here the infrared or false colors means doesn't mean a fake color. Actually, it is the near infrared colors we are discussing. And this color composite translates. The color composition here is important because they are translating the spectral bands which we have collected in multiple wavelengths. At the same time, vegetation is also really important, and it's really near to the same topic of the multispectral multispectral sensors. Although we discussed vegetation and vegetation curve in the first chapter, it is in a kind of repetition, but it's important. Vegetation spectral response, and this vegetation is more relevant to this chapter in this sense of this special this one sensor. That's why we give them touch again. So healthy vegetation has a distinctive pattern in visible. Okay, and why? Because the healthy vegetation is more lighter in the visible range, and due to the red color is absorbed by the chlorophyll or mesophyll, and near infrared and shortwave infrared ranges. Also, they are reflecting in the near infrared and more reflecting because of the leaf structures, and in the shortwave infrared ranges also. Some of the key behaviors, it is visible red color, visible red, low reflectance because chlorophyll absorbs strongly here, and visible green. So visible red is actually nothing but a low reflectance, and the reason of the low reflectance is in the visible red part is actually absorbed by the chlorophylls very strongly. Visible green, higher reflectance, so leaves appear greens. That's why the visible green parts more important and usable in the remote sensing. Near infrared, very high reflectance from the internal leaf structure. We discussed already this above that this distinctive pattern in the near infrared is very high, and the reason is the leaf structures. And in the shortwave range infrareds, it is water absorption lower. Due to the water absorption, they are showing a lower reflectance. So these are some of the key spectral behaviors of the vegetations in the visible red, visible green, or we can also call it the green region, and near infrared or shortwave infrared. So in the shortwave infrared, the reason is why, because the water absorption is lower, the water absorption causing the lower reflectance. So this response enables the vegetation detection. Okay, what helps as the vegetation spectral response mainly, because this helping us enabling the vegetation detection to, that's why we are using mainly vegetation to detect the greenery and health monitoring of the vegetations in line cover classification. Based on this, we are checking the crops health also. In the right side, we have the curves. So we don't see the tree, we see the spectral response, and in terms of the numbers. That is one of the note from these slides. Now this is for third sensor. So for we discussed the CCD and the charge couple device photo camera, and then we multiple spectral sensor, and this is the third sensor, hyperspectral imaging spectrometer, or you can call them hyperspectral imaging sensors. This one was our first one. We discussed the photo cameras and video track cameras, and the cameras collects the visual near infrared scenes, and video cameras also capture temporal sequences. Then we discussed the multispectral sensors, and the third one, okay, here we discussed the true color and infrared false colors. We discussed in the context of the multispectrals and vegetation spectral response, and why it's important, and how they're gonna help us. And the visible red, they are basically low reflectance because the chlorophyll absorb strongly, and the visible green is a high reflectance, so leaves appear the green, and near infrared is it's also very high, and the high reflectance reason is the internal leaf structure, and short wave infrared is water absorption, lower reflectance. Okay, so the short wave, the reason is mainly behind the low reflectance that the water absorbed by the vegetation. And this helps us in understanding the vegetation detection, health monitoring of the crops, and the land cover classification. Now this is our third sensors. It's called hyperspectral imaging spectrometer or sensor. They collect many narrow spectral bands. Before the one which we discussed, the spectral multispectral imaging sensor, that was collecting the minimum bandwidth was like 100 nanometer, but they were collecting few bands like 4 5 bands. This is the one which is collecting almost 100 bands, and with a 5 to 20 nanometers, and producing a special spectral data cube also alongside. So this is more or less similar to the spectral multispectral sensors, but much dense in spectral sampling, and it's really heavy. In the right side you can see certain of images that how many acquisitions they are having it from the certain key positions. So the bands they are using starting from the tens even to the 100, in the bandwidth of the each bands is that about 5 to 20 nanometer, which is very less, and used to in even this is used to investigate the chemical compositions of the matter. very close we are coming into this one. In the hyperspectral example, we can take on the prisma images, and examples of this one is prisma. Okay, we discussed this. uh, this is really important, and this is more detailed and final information capturing in helping in finding of the information later on. Now this is the fourth number one sensor, which we call them thermal remote sensing. Thermal remote sensing estimates the temperature from the emitted infrared radiation. So emitted infrared radiation, we discussed one of them is reflected radiation, and the other one is emitted radiation, infrared radiation. The emitted infrared radiation is thermal, and the reflected radiation is the solar radiation. We discussed already in the first lecture. So these things are really matter as in a foundational stuff we have seen. So we should not be repeated again. The measures temperatures through the infrared radiation intensity. Most common Earth surfaces temperatures emit strongly in the thermal infrared range 3 to 14 micrometers, and 3 to more 10 micrometers they are releasing the thermal infrared range as a to show us the thermal or the temperature of the land. Application cloud top temperature, we can check with this. Sea land surfaces, cloud temperatures can help us to identify the rainfall in the sea land surfaces, to see the evaporation level and temperature, everything. Storm monitoring and heat mapping, these are all the applications of the thermal remote sensing. The thermal images shows temperature related radiation, not normal visible colors. That's one of the important distinction. It is actually the radiation we are capturing and the thermal remote sensing sensors. Example, especially for this case, the Sentinel-3 thermal imagery can map the temperature patterns in the hurricanes. That's really powerful. It looks like in the band 10 or band 9. So we are capturing the thermal information of the land from the very high satellites. All satellites are almost like the LEO, low Earth observation satellites. Microwave radiometers. This is the another type of the sensor. This is also passive. So far sensors we have discussed the CCD sensor, like photos camera sensor, multispectral sensor, hyperspectral sensor, microwave radiometer sensors. These are all of them the passive sensors according to the operation mechanism of the passive and the income. Okay. So the passive microwave instruments sense weak natural emission from the soil, vegetation, and water. This is really powerful in terms of the weak, natural emission they are detecting of the soil, vegetation, and water. So it's really powerful. So the earth materials spontaneously emit a weak radiation at a wavelength between 1 centimeter and up to 1 meter. So this range is very small. So based on the microwave radiometers, as we discussed, even it cannot be affected by the atmospheric effect or window. So there from this that can pass very easily. The intensity and disturbance distribution of emission depends on the terrain properties, especially humidity. Yeah, this is one of the big important factor for the microwave radiometer, that the terrain properties, especially humidity, really matters in the microwave radiometer. The higher the moisture, the lower the microwave radiometers can help us to detect the since the or since the weakened natural emission from the soil, vegetations, and water. Because water, the increasing of the water level in the land cover on the targets, it can distort or ruin the image or the acquisition. Used for soil moisturing mapping. Yeah, this can be used for the soil moisture mapping ocean salinity. We are checking that how the ocean or the salt are the ocean and the soil are salty. Estimation, okay, in terrain characterization, we are doing characterization of the terrains. So we will discuss terrain more in detail. Example of such kind of measurements of the microwave radiometers are the soil moisture in ocean salinity. It's called SMOS, and the second one is soil moisture active passive. These are some of the examples of the microwave radiometers. So water contains strongly affects microwave emissions. We discussed already this, that they are absorbing. If we see in the example of the spectral, uh, if we see the vegetation spectral response in the short wave infrared, the water absorptions can decrease the causing the lower reflectance, because they have water and they are absorbing the signal in the water very easily, so they can go inside the water. That is the main reason. In the right side we have some more details about what is the soil moisture active passive. It's one of the NASA mission, and all of the details are given. Another type of sensor, we call them LiDAR. One of them is radar, radio and ranging detection, and this is the light detection and ranging. If you see from the second lecture, we have discussed the azimuth and the ranging. So azimuth is the direction of the platform, and the range is the direction of the perpendicular to the azimuth, which is measuring the distance from the earth. So this LiDAR product is helping us to create the digital terrain models and digital surface models. And if we see exactly, this is how they are measuring the altitude of the objects or the heights of the objects on the land. So this is an active sensor now. So from this onward, we started the active sensors based on the operation mechanism of the sensor. An active laser and based instrument that measure the distance from the pulse travel time. This is one of the important feature of this one. We will have the below the formula of this one also. The light data, okay, we discussed already. In the active sensor, we have our own emitting device for the electromagnetic waves for illuminating the object on the earth or the target, and the back bounce signals captured by the satellite again, or the active sensors. An active laser based instruments that measure the distance from pulse travel time. So the pulse travel time they are calculating, like they are originating the pulse from themselves, then go back, then go to the target and hit the target. After that, when they are originating back to the sensor, so this is called a pulse travel time. This emits a shaped light pulse and record the reflected signals. So they are recording the pulse travel time, and uses round trip time to estimate the distance and location. This is exactly helping us how to identify the location and the distance of the radar in the exact topic we have discussed in the last lecture of the Earth observation of platforms. Azimuth in the ranging direction. The ranging direction is exactly helping us the altitude of the altitude of the satellite, and the identifying the locations. And the airborne lidar creates a 3D terrain in feature mapping products. That's why we can see such kind of the colored 3D sensing. It is the benefit of the lidar sensor. In the right side, we can also see the colored coded New York point cloud. So it is exactly has been the reconstruction of the airborne lidars 3D terrain. So 3D terrain exactly the sizes or the exactly location. If we see like SVG shape of the Google map, it is exactly the terrain is representing that. So airborne LiDAR creates a 3D terrain and features mapping products. And this is the outcome of this LiDAR sensor. Okay, and the ground-based LiDAR maps atmospheric structure, dust, and pollutants. We are basically having two types of the LiDARs, uh, LiDAR sensor. One of them is ground-based, and the other one is space-based, the airborne LiDAR. So we already discussed. We have ground-based platforms, and we have airborne. We have high-altitude platforms, and we have a space-borne. But the LiDAR detection here, we mentioned it is a airborne LiDAR due to the airborne, because airborne LiDAR is a little bit closer to the Earth, starting from 40 to 150 kilometers. So ground-based LiDAR maps atmospheric structure, dust, and pollutants. So they both have the airborne LiDAR and the ground-based LiDAR have its own benefits. So the one from the ground-based, we are mapping the atmospheric structure, dust, and pollutants, but from the airborne lidars we are creating a 3D terrains and feature mapping products. So the main output of the lidar product is the digital terrain model and the digital surface model in 3D point clouds. So we have here the formula of the distance, how it's calculated, the speed of the light. We know from the first lecture the speed of the light is roughly 3 multiplication 10 to the power 5 kilometer per second, and multiply by the round trip time divided by 2. So this is exactly giving us the distance. Another sensor, it is radar altimetry and precipitations missions. Both of them are relevant. Radar altimeters are the sensor, and the precipitations measures are basically using for the and these are basically two missions launched. One of them is GPM, and the other one is TRMM. And TRMM is the tropical rainfall of the measuring um, tropical rainfall uh, measuring. This is one of the machine launched by, exactly forget about its complete abbreviation. And this is one of the mission launched by, combined in 1994 by the NASA in Japan, and the GPM is the Global Precipitations Monitoring Missions. It is the follow-up missions launched by, again, by the NASA, the Japan Aerospace Agency. So this is basically helping to understand about the rainfall structure, the exchange energy, and all this stuff. So what exactly radar altimeter do? The active microwave system measures elevation profiles. It is really important. These radars altimeters can be a little bit different from the radio microwave. If we see in the radio microwave, in the light detection and ranging sensors, they are basically creating the digital surfaces or the digital terrain models. And the one which we are discussing is the radar altimeters are the active microwave system measure the elevations. They are measuring the highness or altitude of profiling in rainfall structures. Okay, if we see the radar altimeters, we have not discussed further this. The radar altimeters are readings over images shows varying intensities of radar reflections from the lag in surrounding land. In the cryoset is able to measure water surface elevation for the full extension of the lake and even track the lake basis slopes. So if we see the same picture, they are showing us the radar altimeters are helping us based on the microwave systems to measure the elevation profiles. and it is a little bit different from the LiDAR sensor, and doing they are basically doing the elevation profiling, and that one is basically doing the light detection and ranging. So this is the main differentiation of between both of them. And we discussed some of the missions of the precipitations of the global precipitations missions of 2D and 3D, TRMM, and the other is GPM Global. So both of these are the missions which has been launched, and GPM is launched in 2014, and this is the more advanced versions of the TRM or its follow-up missions. So normally the precipitations missions, the radar altimeters are actually helping in these rainfalls and all these uh, the temperature or the climate issues. So these precipitation missions are usually are equipped with multiple sensors of the microwave like and visible imaging and all of the types radars and microwave, all of them, because they need all of the sensors to operate in this kind of missions against means the same platform we were discussing, and the platform is equipped with all of these kind of sensors. Imaging radar, an active microwave imaging systems for cloud penetrating and all weather earth observation. The imaging radar is also helping as the weathers of the earth observation, and it is exactly an active microwave signals. And the imaging radar is also an active radar, an active sensor, operates at a wavelength between 1 centimeter and 1 meter, sensitive to the humidity, conductivity, object size, and surface roughness, can penetrate clouds and work without the sunlight. And we already discussed that the active sensors are usually working without the sunlight. It supports dimensional sensing through the interferometry and tomography, and support polarimetric sensing and for rich target characterization. This is the features of the imaging radar, and it is an active microwave imaging system for cloud penetrating. The good thing is like they can penetrate the clouds. That's why it is using for the imaging radar, so it cannot be affected by the atmospheric effect or atmospheric window. The optical images shows reflected light. Radar images shows microwave backscatters. It is a little bit, you can call them like the cons of this one. As they said that the optical images shows reflected light, but the radar images shows the microwave backscatter basis they are using. So this is called imaging radar, and which can easily penetrate the cloud, and they are helping in the earth observation of the weathers, and it is very very close in terms of the wavelength. If we see it's 1 centimeter to 1 meter, but in the same case it is again sensitive to the humidity, conductivity, and object size and all the surface roughness, because in the case of the rough surfaceness, we know it can happen the diffusive reflection, which can again cause that they can send the electromagnetic signals in multiple directions. But the good thing is they are supporting 3 dimensions of sensing through the interferometry and tomography, and supports polarimetric sensing and for richer target characterization. In the right side, we can see some of the imaging from the Sentinel-1 and Sentinel-2 compared with the optical Sentinel-2. Imaging and non-imaging. So we already discussed the imaging radar in the previous. And here we are doing the comparisons of between both of them, the imaging and non-imaging. In the pixels, what is the pixel? Pixel is nothing but a short, it is a unit of the picture. Imaging and non-imaging, remote sensing data as a numerical measurement first. Images are visualized of those numbers, as we already discussed this in the start. So imaging sensors like cameras, scanners, thermal images or imaging radar, data can naturally be represented as an imaging. That's why they call them the imaging radar. But in the case of non-imaging radars, the static positions are not the actual images. So that's why they are using altimeters and profiling lidars and scatterometers. So exactly here, if you see, the altimeter is also doing the same. They are capturing the information of the uh, elevation profiling or LiDAR profiling and scatterometers. So data are profile measurements or parameters rather than the direct images. Exactly, this is what happening in the non-imaging sensory, and it is based in this is one of the main categories we are categorizing the sensors. We have seen that that can be imaging radar or non-imaging. In the imaging, we have clearly scenes like the CCD, type of sensors, charge coupled devices. So they are say like cameras, scanners, thermal images, imagers, imaging radar we already seen. So data can be naturally directly represented as an image. But in the non-imagery case, if we see the altimeter radar, so altimeter radar is directly now coming under the non-imagery radar. So this is a short comparison of both of them. And profiling LiDAR is also again coming under this one. Because based on the profiling LiDAR, we are detecting the light and range, and we are checking the distance of the satellite and the finding the locations also. So in due to this one, we are making as an output of the LiDAR digital surface model and digital terrain models. We already seen this, and scatterometers. So here what is happening exactly, that is not directly in the form of the picture. It is exactly the numbers or measurements, and due to the emittance or electromagnetic rays, and after that these numbers have been converted to information. So data are profiles here, and measurements or parameters rather than the direct images. And what are the pixel? Pixel, small image element plus the numerical value. The pixel is actually in a picture is representing a number which shows the color. Visualization translate numerical matrices into gray values or colors. Later on, when we are applying to these uh, data which we have captured, like data are profiles, measurements, or parameters rather than the direct images. So later on that these are numerical matrices are then converted into the gray values or the colors. Then based on that we are representing, making the non-imagery sensor records as an imagery to understand the information from them. So this was the whole idea about multiple type of sensors we have seen so far, the Earth observation instruments. So these are main instruments, and we have seen the categorization, the sensor, and active passive, and along the active passive, we have seen in the multiple domains, near infrared, microwave, and another categorization method of the information collected in the imaging or non-imaging radar. So we have seen all of them, and the next lecture will be about the remotely sensed data, and that is the new glance on this whole course, which is the intelligent sensing and remote sensing products, or you can say the remote sensing products. So the fourth lecture will be starts soon. Thank you. Bye.